Hello, hello. Um, Today is going to be a recap from one of last year's sessions, and this is a small briefing about how springs work in physics. This will cover most of what you need to know for Physics 1 in terms of simple harmonic motion and like Hooke's law. We will not go too far into Physics C, although a lot of the concepts are similar. So to begin with, a spring is an elastic object that's typically made from metal that stores mechanical energy, which is basically when a spring is stretched, this tension holds energy, holds potential energy, and when it's let go, the spring will compress, right? It will revert back to its equilibrium state, or back to a more pressed-in state. And this movement is basically potential energy turning into kinetic energy. Springs are typically made from steel, and in everyday terms, uh, a spring is almost always a coil spring, which is the kind of spring that you can see on the right of the slide. But there are other types of devices that can be considered as springs in physics. In physics, a spring is defined as a system that tends to return to its equilibrium position when displaced from that position. There's a couple of types of springs. There's two types actually. You have your ideal spring, which is your default type of spring. It's very rarely will you ever encounter a real life ideal spring, but we tend to use this for theoretical purposes in physics. This ideal spring has no weight that has to be accounted for in your mechanics equation, no mass or damping losses. The force exerted by the spring is proportional to the distance the spring is stretched or compressed from its equilibrium or relaxed position. You will typically see ideal springs drawn as coil springs in physics diagrams. Non-ideal springs are more realistic. They're like the normal springs that you'll encounter, and this is where the spring constant, or the amount of force needed to pull the spring by some amount, is not a constant number, and it depends on how stretched is the spring. Examples of non-ideal springs that are not necessarily coil springs include rubber bands and bungee cords. Although you will not have to do this in Physics 1, but as a trivia, if you wish to find the potential energy of an elastic spring that has been compressed or stretched to some displacement, you have to actually find a function that defines the force and then integrate it with respect to displacement. One of the most important laws regarding ideal springs is Hooke's laws. Hooke's law applies to every ideal spring. It does not apply to springs that are not ideal. But what it says is that the force needed to extend or compress a spring by some distance x scales linearly with respect to that distance, aka the force needed is k, which is some spring constant, times x. So k is known as the force constant or spring constant. It is a constant and is measured in newtons per meter. This varies depending on the type of spring and different characteristics of the spring. X is displacement from the equilibrium position. Equilibrium position, I've said this a couple of times, but I haven't really defined what it is. Equilibrium position or rest position is defined as when the spring is located without any external force. Basically, a point where the spring experiences no net force and just stays in the same state that it is, aka resting. Elastic limit is not something you'll meet in Physics 1 or C. but it deals with the idea of stress. Elastic limit is the maximum displacement before the spring could stretch to before it becomes permanently deformed or even breaks. So in other words, once the spring reaches beyond this elastic limit, the spring will no longer return to its original shape and Hooke's law will no longer hold. You can think about this as like with a rubber band. Like if you stretch the rubber band way too much, it'll eventually snap. You can't like return it back to like the original like state of the rubber band or spring. This is kind of like an experiment to demonstrate this correlation between displacement and force. You can see it's a direct linear relationship. This plot basically follows a single line of fit, and the slope of this line will be the opposite of the spring constant, or negative k. Why is it negative? You can think about it like this. Imagine you have a spring that's lying horizontally, right? And you define like right as positive, and so you stretch the spring to the right. So the displacement is positive. Since the equilibrium position is to the left of your stretch, like the edge of your stretch spring, you know that once the spring is released, it has to travel left. It has to accelerate left. So therefore, even though the displacement is right or positive, the force has to be negative or like directed towards the left. So you have to put a negative sign to account for that. So in this experiment, you can see it's not like what I said where it will be directed towards the right. Here it's directed towards the left, and we define that as a negative displacement. But you can see the spring force is directed right, so it's all positive measures. Dividing these two gives you like a line of about like 640 as a slope. So therefore, this 640, it could represent the K constant, or 640 newtons per meters. Potential elastic energy is a type of potential energy. So up until now, you've probably heard of gravitational potential energy, which is basically the potential energy something gets if you raise it to some elevation, and this comes from like the gravitational pull towards Earth. You've possibly heard of electric potential energy, which is the same thing as gravitational, except it's electric force that's attracting charges together. So there's different types. Here is a separate type of potential energy. This is elastic energy, or potential energy that is stored by spring. So when compressed or extended, like we said before, a spring can store energy. This is called potential energy, and this can be converted into kinetic energy and work. The potential energy of a spring is given by the formula U is equal to 1/2 of kx squared, or here it's written as PE, but typically energy is denoted with a capital U. K is the spring constant of the spring, and X is the displacement, or like the amount, or like the lengths that the spring is stretched. Springs can oscillate or like bounce back from like an equilibrium position to another position. So for example, if you like press on a spring, it can like boing it, and during this like motion, you can see it like bounce around multiple times. This occurs because of a constant shift or conversion between potential and kinetic energy. At its most compressed point, once you release it, the spring will change direction and start to accelerate towards the equilibrium position. So it will start to exchange PE, or potential energy, for kinetic energy due to conservation of energy. It then reaches its natural lengths, but there's still a bit of momentum, so it will get pushed a little bit further. It compresses again. Then it will begin to slow, as kinetic energy would slow down, and potential energy comes up again because the displacement from the equilibrium increases. And after that, there will be a force attracting to the equilibrium again. And then so it will just keep on moving for multiple times. So I referenced conservation of energy, and we typically have used this beforehand. We've kind of used this to determine certain characteristics of objects that are acting under the influence of gravitational force. But the general conservation of energy holds for every single type of energy, not just gravitational. Unless there's external work being done on a system, for example, like friction taking away work from a system, the total energy has to be conserved. And all the changed energy has to be converted into outside work. So we can write this equation as K1U1 is equal to K2U2. K represents kinetic energy and U represents potential energy. So what this is basically saying is that the sum of the total amount of kinetic energy and potential energy at the beginning, or in an isolated system, before and after some type of motion, the sum of kinetic energy and potential energy has to be a constant number. I think we have previously done a briefing on the work and energy unit, but in case you didn't go to see that, here's a quick review. So kinetic energy is the energy of motion. When something is in motion, it has kinetic energy, and it's given by the formula K is equal to 1/2 of mv squared, where m is the mass of the object and v is the velocity of the object. Gravitational potential energy was the other type of potential energy that I referred to earlier on, and this is stored energy that's associated with an object's height above the ground. So when you place something that's when you place something above the ground, there's again force that's trying to pull it towards the center of the Earth, and this causes the object to have stored energy. So you release the object, it will naturally fall down. We typically write this as UG, G representing gravity, and it's given by the formula NGH, or here it's MGY. M is mass, G is your gravitational acceleration. On Earth, it's about 9.81 meters per second squared, and Y is just the height above the ground, or displacement above the ground. Today we talked about electric potential energy, which is stored energy associated with a stretch or compressed spring, and work is the transfer of energy in and or out of a system by an external force. In order for work to be done, there has to be an external force. Work is given by the formula force times distance. This is assuming that the force and distance are directed in the same direction. So like if, for example, if you are pushing something across, like the floor was a certain amount of force, you're exerting work on that object because you're pushing it and it's moving in that same direction. In cases where force is like directed against the distance the thing is traveling, work is negative. So it becomes negative magnitude of F times D. If in physics C, this is the formula for physics 1, but in physics C, you will learn that work is actually can be expressed even more precisely. It is the dot product of the force vector and the distance vector, or the displacement vector, if it's done in 2 dimensions. This would mean work would be equal to the magnitude of the force times the magnitude of the displacement times cosine of the angle that forms in between those two vectors. So let's look at problem 1. We're going to consider a spring with negligible mass that has an unstretched length L0 of 0.088 meters. Here we have a block with mass of 0.15 kilograms, and it is suspended from one end of the spring. The other end is fixed, so this wouldn't move, and all of the spring's force and motion would be due to like the block. When we initially put this block on the edge of the spring, it will fall down. It will like stretch the spring and it will bounce up and down, like I said earlier on with the example of like pushing it in. Here it's stretching it out, but the same thing happens. After the thing settles, there will be there's a new stretch length of the spring, because in total it stretches a little bit more due to the weight of the block. And this new length of the spring is 0.098 meters. Assume this spring is an ideal spring, in which case it satisfies Hooke's law. This problem is asking for the spring constant. So we could talk, we could start analyzing forces, right? So we know that like the net force that's exerted on the spring and the force that is causing it to stretch has to be the gravitational force between that block and the Earth, which can be written as mg. So here we have F1 is equal to negative mg because it's directed down, and we're assuming down is negative. There's also a opposite force that's directed upwards. That's like the force that's trying to like pull the spring back to its equilibrium position, right? So we'll call this F2, and this is what we are trying to look for. By Hooke's law, the magnitude of the spring force is K times the displacement. We know that we were already given a length for the equilibrium position that was 0.083 meters, and we were also 0.088. And we also have a final length of the spring, which is 0.098 meters. So this change in length has to be L final minus L initial, and that will be your X value for Hooke's law. And then you obviously have to multiply this by K. This will give your force exerted on the spring. Since we know that the spring has settled, it is in static equilibrium, aka nothing is moving. So because nothing is moving, nothing is accelerating. And so the sum of the forces is 0 by Newton's second law. So we can write F1 plus F2 is equal to 0 because there's 0 net force. So we can write negative mg plus k times L minus L0 is equal to 0. Moving mg onto the opposite side gives k times L1 minus L0 is equal to mg. Divide by that difference in order to get k. So you have k is equal to mg over L minus L0. All of these values are already given, so we can just substitute them in. M is 0.15, g is 9.8, L is 0.098, and L0 is 0.088. So if you plug that into a calculator, we will get k is equal to 147. So any questions? Okay, I'll take that as a no. Our second problem is as follows. A body of mass m is suspended from a spring with spring constant k. In this configuration, you can see in part 1, and the spring is stretched 0.1 meters. So if two identical bodies of mass m over 2 are suspended from a spring with the same spring constant k, but in a different configuration, this is denoted with the second figure. They're asking how much will the springs stretch? So here again we can use force analysis. So again we have the gravitational force that's exerted on the spring is the same as the weight of the object. So we can write that F sorry, F1 is equal to negative mg, and the force between the body and the spring obviously is kx by Hooke's law. So you can substitute this in the formula F1 plus Fs1 is equal to 0 because everything's in static equilibrium for both parts. So we get a negative mg plus kx is equal to 0. Solving for x in this equation yields that x is equal to mg over k. We also have to do it for the second figure, right? We know that this x is 0.1, so we're just trying to find a stretch length, like a displacement for the second part and relate it to x. So here, because the mass is not the same, has equals in minus m over 2g because the the masses have been halved. But we still have Hooke's law apply because this k is the exact same and both springs are ideal. So we can rewrite this we can rewrite that the formula that the net force is 0 as this and can again substitute in values here. As you can see, we have to keep in mind that this is over 2, but the second term remains the same. Solving for x2, similar to the first figure, reveals that x2 is m over 2g over k. We can compare this to mg over k and see that the only difference is that this thing has an m over 2, aka x2 has to be 1/2 of x. Therefore, we just do 0.1 and then divide this by 2, so we get 0.05 meters as our displacement. Any questions? Okay. Here we have 2 springs that are attached to a block that you can see below. They have different K values though. This one has a K value of 120 newtons per meter, and this one has a K value of 80 newtons per meter. And they're attached together, so we have to find the total amount of force required to move this outer block inwards by 10 centimeters. So imagine this for like 10 centimeters. It moves inwards. 10 centimeters is 0.1 meters. So we will use that in all of the calculations. So this is kind of like a special case in which because the 2 springs are working in accordance with each other, we have to actually be able to basically exert enough force such that both springs will compress by a meter. So we actually just add up the K values in order to get like your total K value of the 2 springs together. So we add up 120 and 80 and we get 200 newtons per meter. And by Hooke's law, we know K delta X is equal to F. So we multiply 200 by 0.01. So we have 2 newtons as the force that we require. So takeaway from this problem is that the force that's required to compress or extend multiple springs that are like in a row or like attached to 2 blocks, it's just the sum of the forces to compress and extend each spring individually. So this is kind of like you can think about this actually like circuits, but we're not going to go that far right now. In this arrangement, the springs are said to work in parallel. Obviously, you have a contrast. This is contrasted with working in series where you link springs together in between the blocks. in which case this formula does not apply and you have to use another one. Okay, a 42-kilogram teenager balances on a pogo stick, causing the string in this with the spring, sorry, in the stick to compress downward by 0.18 meters. Determine the elastic potential energy of the teenager. So we have our M, which is the teenager, and we have our X, which is given in the problem. So again, we can use force analysis. We know that there is, again, no net force when it's stretched to its max value. So so we have Fg is equal to Fs, or like the magnitudes at least. To do this, by the formulas, Fg is equal to mg and Fs is equal to negative kx. We get mg has to equal to kx in order for the net force to be 0. Oops. We can solve for k here because that's like one of the things we don't know. So we just divide by x on both sides, so we get k is equal to mg over x, and we can substitute in everything that we know from before. And we get k is about 2.29 times 10 to the power of 3 newtons per meters. To calculate the elastic potential energy, we use the formula 1/2 kx squared. So since we know k, we know everything here that we need to know. So we just plug in everything and get 37 as the answer. So 37 joules is the answer. So this problem needs a bit more than just like your normal force analysis that we've been doing so far. You have to know a bit of kinematics, but we can still try it. So we have two children that are playing a game in which they try to hit a small box on the floor with a marble fired from a spring-loaded gun with an ideal spring, and that is mounted on a table. This target box is 2.2 meters horizontally away from the edge of the table. So we're assuming that this gun is mounted at the edge of the table. Bobby goes first and compresses the spring by 1.1 centimeters, but the center of his marble falls 27 centimeters short of the center of the box. This question is asking how far should the second player, Rhoda, compress the spring to score a direct hit. So obviously, since we're dealing with compressed springs, we can actually use energy as the main way to analyze this problem. So energy is obviously 1/2 of kx squared because what we're looking at is potential energy stored in the spring. So that's potential elastic energy. We know that Bobby's marble speed at the end, let's say if we call this V, the kinetic energy right before like the marble hits the ground is 1/2 of mv squared. So we can set these to equal to each other because throughout this entire process of like this ball launching from the launcher into landing on the floor, we're assuming that there's no such thing as like air resistance or like work done by the air against the ball. So we can use conservation of energy. In this case, all of this elastic potential energy is converted into kinetic energy. So we can set 1/2 of kx squared is to be 1/2 mv squared. The 1/2s cancel, so kx squared is equal to mv squared. And here we're trying to solve for v. So v here, if you had to express it in terms of displacement, which we know, m and k, we get v is equal to x times the square root of k over m. and we know that x is 1.1 centimeters. Since we have to look at this through a kinematics perspective as well, the next relevant thing, since we're mainly considering horizontal distance, because that's given, is to look at t, or time, because that gives you position. Vt gives you position. So we know that by the kinematic formula relating height, initial velocity, sorry, not height, displacement, initial velocity, and acceleration, we know that delta x is equal to v initial t plus 1/2 of at squared. Here, v initial is 0 because it fires from rest. A is the gravitational pull. The acceleration of the ball is due to gravitational force, so A is equal to g. And then we're trying to get t. We know delta x because we know that Bobby's marble falls short, so we can solve for that. Delta x is equal to 2.2 meters minus 0.27 meters, aka 1.93 meters, which is equal to v times t. So we're gonna leave it like that for Bobby because we can use these variables later. And we're now gonna look at Rhoda's launch. So we're gonna say she compresses the spring by a certain displacement x2, such that the marble is given a speed v2, where if the marble travels at that speed, it will hit the box directly. So we can use the exact same kinematics formula and get that the displacement again has to equal to 1/2 of g times t2 squared. So here we know that t has to equal to t2 because t does not rely on like this initial velocity because the initial velocity is directed horizontally. In terms of, if you look at this shot, like purely from a vertical perspective, for Bobby's shot and Rhoda's shot, both things start from rest and accelerate at a rate of g towards the Earth, and they fall the same height. So it should take the same amount of time for the balls to hit the ground. Therefore, t has to be the same for both cases. So we know t is equal to t2 then. And we know this time delta x2 has to equal to 2.2. So we set v2t as delta x, which is equal to 2.2. So we know vt is 1.93 and v2t is 2.2. So if we divide, the t's will cancel, and we actually have a ratio of v2 over v, which is 1.14. This ratio has to be the same as the energy. So we will set sorry, this is not energy. This is a formulas for v. Because v2 over v is 1.14, you can say x2 times root k over m over x root k over m is 1.14. So so these are just substitutions for v. And square root of k over m both cancel. It's the exact same spring, and the balls are the same as well. So m and k are the same thing. So we can reduce this entire thing as to just x over x is 1.14. So Rhoda has to compress the spring by an amount that's 1.14 times the amount that Bobby compressed it. Bobby compressed it by 1.1 centimeters. So you multiply that by 1.14, you get 1.25 about. So that's it for this session. So if you have any questions, feel free to ask me. Thank you for attending this session of Logic 7 Physics, And if we have no questions here, I hope to see you next time. So, thank you. Okay, it looks like no one is here, so I will end the meeting now.